Okay, here is a situation. I've got a ground-based observer, an Earth-based observer here, and I've got this guy flying by on his spaceship. The spaceship is moving 0.9 c. Now that's according to the ground-based observer. Of course, according to this guy right here, he's just sitting in a spaceship. He's at rest with respect to his own reference frame. And so this guy here, he gets his little gun out and he shoots a bullet. It's target practice. And he shoots a bullet. And from his perspective, from the perspective of the person in the spaceship, he sees this bullet moving in this direction at 0.95 c. The question is, how fast is the bullet moving according to this person on Earth? The person on the spaceship sees it moving away from them at 0.95 c. How fast is it moving according to the person on Earth? Now, notice if we just did Galilean velocity addition, well, then we would get 0.9 plus 0.95 is 1.85 c. We would get 185% of the speed of light. Well, we haven't talked about it in this chapter, but you've probably heard elsewhere in your regular life that the speed of light is sort of a cosmic speed limit, that no physical object, not even information, can travel faster than the speed of light. So, obviously, 185% of the speed of light doesn't work. We need a better idea. We need a new technique to figure out how fast the bullet is going according to this observer right here. Well, what we need relativistic velocity addition. And so we're going to use these equations right here. And what we're doing here, let's be clear, again, we're trying to figure out if one person, one observer in a certain reference frame measures something, then what does the person in another reference frame measure? So let's be real clear here. What we're trying to do is a transformation. We're trying to transform velocities from one reference frame into another. Well, we've got this person here on Earth. That is our S reference frame. The moving reference frame, or the primed reference frame, is right here attached to our spaceship. This is the S prime reference frame. So in this case, we know what the velocity is in the primed reference frame. We want to know what the velocity is in the unprimed reference frame. We need relativistic velocity addition. And so here it is. Again, the primed are the velocities of an object in frame S prime. And again, we're using U for the velocity of the object, and we're using V for the velocity of the reference frame. And do notice that if either U or V is much less than C, then this term right here becomes very small, basically goes away, and we're left with Galilean velocity transformation. So this is why you don't notice this in your everyday life, is because the velocities that you deal with in your everyday life are so slow that we don't have to worry about this stuff, right? So if either V or U is, sort of human-sized speeds, then the Galilean velocity transformations that we started this chapter out with work just fantastically. Okay, so in this case then, let's apply this terminology to this case right here. In this case, the velocity that the primed reference frame is moving with respect to the unprimed reference frame, well, that velocity is 0.9 c. We know the velocity of the object in the primed reference frame. So we know U prime. That is 0.95 c. And I'm asking for U, or I asked you what was U. And so this is, let's do this as an example. Here it is in black and white. A rocket flies past the Earth at precisely 0.9 c. As it goes by, the rocket fires a bullet in the forward direction at precisely 0.95 c with respect to the rocket. What is the bullet's speed with respect to the Earth? And so what we want to do then is we want to use the velocity transformation to find U if we know U prime. So this is the equation we're going to use. Okay, our U prime, 0.95 c. V is 0.9 c. And again, here we go, we got the 0.95 c times 0.9. And again, notice in the denominator here, our c's cancel, so we don't have to run our calculator for that. I'm going to have to run my calculator for the rest of this, though I definitely can't do that in my head. When I do that, I get 0.997 c. Okay. So, very fast, certainly. It's satisfying that it's not greater than c. Right now we're at 99.7% of the speed of light, so that is very fast. But at least it's not faster than the speed of light. That is a good thing.